Alrighty. What we're going to talk about now is another really important subspace. Well, actually a few. We're going to be talking about the null space or the kernel and something else that's called the image. So before I do this, let's think about what a matrix is doing, okay? So let's say we have a vector X in Rn, okay? So we have this vector X that's living inside Rn, and basically what this is, like X1, X2, all the way through Xn. And when we have this vector and we apply a matrix to it, AX, let's let A here, this is going to be an M by N matrix. If you'd like to see it in coordinates here, I could say A11, A1N, blah, blah, blah. We've done this a lot, right? And if you'd like to see it written explicitly. Well, when we take the product A times X, you can think about this as you're using A as a function, right? If you have like X in R, well, and if you apply a function F to X and the output is some Y, what F is then doing is F is a function that took in a real number and spit out a real number, right? And this notation, this function notation here is very, very common and standard. And what this is saying is it's saying that F is a function that the input is a number, a real number, and the output is a real number, right? It's a function, right? And so we can think about a matrix as a function also. We can think about we can think about a matrix being a function where the input is an n-dimensional vector. So, right, the input is going to be an element of Rn. And what is the output, right? Well, we usually see this as like AX equals B. And the output B here is usually like B1 through Bm, right? And if you'd like to think about this, A is an M by N matrix, X is an N by 1 vector. When you multiply those together, the result is an M by 1 vector, right? And B, in this case, is an element of Rm. And so we can think about a matrix as a function from n-dimensional Euclidean space to m-dimensional Euclidean space, right? And this is a really, really important concept here, is to understand that matrices are actually just functions that's taking elements of n-dimensional space as an input, and then as an output, it's sending those to some element of m-dimensional space. And so we can really think about, right, what is this doing? A takes X as an input and gives you a vector B as an output. Now, we can understand a matrix as a function in this way here, right? And because we can understand a matrix in this way, we can talk about subspaces. So let me give you some kind of notation and definition here. So here's some notation. A function that takes an element can't spell here, takes an element from X to an element from, let's say, an element in X to an element in space Y is written as, and so we say F is a function from X to Y, right? Where here X and Y are spaces. Like we could say Rn, Rm, right? But in general, these will just be spaces or maybe subspaces, right? We call X the domain, and we call Y the codomain. You may also see the domain written as the source and the codomain written as the target, right? You can think about F being a function that is taking elements from a source space X and sending them at a target space Y, right? Usually we refer to these as the domain or the codomain, but you may hear me refer to these as the source and the target, maybe a little more informal. Okay, now with this notation here, when you have a matrix A that's a function from Rn to Rm, there are two very important subspaces. A subspace of the domain is called the kernel. And a subspace of the target is called the image. And so in words, this is the kernel of the map A. We'll also refer to a function as a map or map. And you could read this notation as F maps X to Y, right? You could also say F maps X to Y. This is another way we could see or understand this notation here. So this is the kernel of the map A, and this is the image of the map A. Now, the image is something that lives inside the codomain, and the kernel is something that lives inside the domain. So let's understand what these are. And this is these are definitions here. The kernel, which is also referred to as the null space of A. Maybe I should have specified. So null of A, which is the kernel of A, is the following set. It's the set of vectors in Rn such that when you apply A to those vectors, you get the zero vector in Rm. So maybe I should say like 0M there to specify that these are vectors in the domain that when you apply the function to them, they get mapped to 0. So the kernel or the null space is looking at everything that is sent to 0, right? It's because it's the kernel. What about the image? The image is everything that A hits, basically. And if I was looking at this in B, this is B in Rm such that AX equals B, right? And so what the image is it's what shows up, right? It's everything that gets mapped to under this function A. So you could think here, if you'd like a little picture, we have A. here's RM, or Rn, excuse me, and it maps this to Rn. Rm, I'm getting them backwards. So how A works is it's going to take elements of Rn and it's going to map them somehow over to Rm. And it doesn't have to map them to all of Rm, right? It could map this whole space to just like a subset of Rm here. And this subset, this is called the image, right? It's everything that A takes an element to, right? It doesn't have to be the entirety of Rm. Sometimes it is. And those are special types of functions. We'll explore this more in depth later. But then what's the kernel? The kernel is if you have in this image, you have the origin here. This point's going to be the origin. And the origin is the 0 vector, right? Well, the kernel is everything in the domain that gets sent precisely to the origin, right? And this would be like the kernel of A. And so these are very, very important subspaces. You can learn a lot about a function or the behavior of these spaces based on how you transform one space into another. And we'll look at this a lot more. The next chapter is called linear transformations, and we're basically going to try and understand more of what's happening when you transform one space to another, like what's going on here, right? And so this is just to give us an idea of what these subspaces, the kernel and the image, what these actually are. Okay, cool. Let's look at a theorem with regard to the kernel, and then let's see if we can do some examples here. Okay, theorem. Let's let A be an M by N matrix with the rank of A being R. Then there are N minus R, so the N minus R solutions to AX equals 0 is a basis for the null space or the kernel of A. And moreover, the dimension of the kernel of the matrix A is N minus R, right? Well, that's because if you have N minus R solutions and those vectors form a basis, well, then that's the number, then that many elements is going to define the dimension of the kernel here. So let's look at an example finding the kernel and image of a matrix. So let's let A be the matrix 1, 2, 1, 0, negative 1, 1, 2, 3, 3. And we want to find the kernel of A and the image of A, right? Let's start with finding the kernel. Well, to find the kernel, we need to set up the following equation. If we let X be X1, X2, X3, right? This is a 3 by 3, so we know both N and M are 3. So here we have X, which is X1, X2, X3. We're looking for these vectors such that AX, so the matrix A, X1, X2, X3 is mapped precisely to 0, right? we want to find those vectors X such that this is true. So how can we do this? Well, we can set up a system of equations corresponding to this system, right? That would be 1, 2, 1, 0, negative 1, 1, 2, 3, 3, 0, 0, 0, right? And then you solve this, you put this augmented matrix in reduced row echelon form to find a solution. We know how to do this. This matrix is pretty easy. And so we can just see what we get is 1, 0, 3, 0, 1, negative 1, 0, 0, 0, and then 0, 0, 0. So this is the reduced row echelon form. Now, in terms of a solution to this system, what does this tell us? Well, this tells us x1 plus x3 or 3x3 equals 0, right? And then it tells us x2 minus x3 equals 0. And the last equation tells us x3 equals x3. So if we give this a parameter t, then we have that x, the solutions, there's an infinite number of solutions here because we have a parameter. This is going to be negative 3t, right? Like, so here, let's say we have parameter t for t and r. So we have negative 3t, t, t for t and r. So that means we can write these x's as t times negative 3, 1, 1 for t in R. But what this means is the solutions are spanned, right? It's just linear, or it's just scalar multiples of this vector negative 3, 1, 1. So for that reason, then the kernel here is going to be the span of the vector negative 3, 1, 1. Like this, right? We found those vectors X such that when you apply the matrix A to them, you get the 0 vector, right? So these are precisely the vectors that get sent to the origin under the map A, right? Under the matrix A. It's those that are scalar multiples of the vector negative 3, 1, 1, right? These all map to 0 under the matrix A. Well, how do we find the image? The image is just everything, right? The image is basically, you're going to think of it as the column space because it's everything that this matrix is mapped to, right? You're looking at everything that when you apply this matrix to X, you're looking at all outcomes, right? So the image here is really just the column space of A, which is, and let's go back to our reduced row echelon form to find the column space here, right? Well, we have the 2 pivot rows, and then we look at the pivot rows of the original matrix. So those are going to be spanned by the vectors 1, 0, 2, 2, negative 1, 3. So this is the span of 1, 0, 2, 2, negative 1, 3. Cool. So this is usually how you calculate the kernel and the image. So to find the kernel, you always set up AX equals 0, solve for X. Then once you solve for X, you can usually write it as a spanning set, right? And similarly for the image, you just look at the column space. And the column space, because that's the image of the columns, right? And so, excuse me. So this is usually how we find the kernel or the null space and the image of a matrix A. Let's do some quick vocab here. We will call the dimension of the kernel, we'll refer to this as the nullity. So if you ever hear me say like the nullity of the matrix A, what I mean is I mean the dimension of the kernel of the matrix A, right? But mathematicians are lazy and we elect to take a shortcut whenever we can. So we'll just refer to this as nullity instead of dimension of the kernel of A, right? With that being said, we have a very, very important theorem, and it's called the rank nullity theorem. The rank nullity theorem says that if A is an M by N matrix, then the rank of A plus the nullity, which is the dimension of the kernel of A, is always N, right? In here. Let's verify this in our previous example. We are looking at a 3 by 3 matrix. So we would hope that the nullity plus the rank is 3. Well, what's the nullity here? Well, what's the dimension of the kernel? The dimension of the kernel of this particular matrix is 1 because it's spanned by, it has one basis vector, right? What's the rank here? For the dimension of the image of A? Well, it's 2. 2 plus 1 is 3. So you always have that the dimension of the kernel plus the dimension of the image is always N, right? If you would like to see this differently, you can write this because the rank is really just the dimension of the image, right? So equivalently, the dimension of the image of A plus the dimension of the kernel of A is N. This says rank plus nullity equals N, right? And this is a very important theorem. I honestly, I would not be surprised if on the final, I just asked you to state the rank nullity theorem. This is an important theorem, and it's something that we'll definitely want to make sure that we know and understand. Okay. So basically what I want to do for the remainder of the video is I just want to list 2 theorems that it's just kind of a word vomit of equivalences, but they're important to record and kind of understand what these things are saying. So I think to wrap up this video here, let's just look at a couple really important theorems that we get from just knowing the rank nullity theorem, right? So this isn't Green's theorem. I'm not going to use Green theorem. The following are equivalent for the M by N matrix A. Okay, we have that the rank of A is N. So basically what we're saying is all of these statements here are equivalent to saying that the matrix A has max rank, right? Because if we have rank N, then that means the dimension of the kernel is 0, right? And so that means we have max rank. And so the dimension of the image is the dimension, like maximum dimension here. Well, then we have, this is equivalent to the row space of A being Rn, right? And that's because the kernel is 0. So we have a maximum size space here. We have that the columns of A are linearly independent in Rm. We have that A transpose times A is an N by N invertible matrix. We have that there exists an N by M, the flip here, matrix C such that when you multiply A by C on the left, you get the identity in Rn. The last thing that all of these statements are equivalent is if AX is 0 for some X in Rn, well, then that implies that X is the 0 vector. And this last one here, this one also makes sense kind of immediately, right? The rest of these you'll have to kind of think about on your own a little bit to really understand why these all imply each other. But this one we also see immediately, because if the rank of A is n, well, then the dimension of the kernel is 0, which means the only thing that's getting mapped to 0 is 0. And that's exactly what statement 6 is saying there. It's saying, well, if you have something that maps to 0, then that thing itself was actually just 0 because we have max rank. Okay. Now, let's do a similar theorem here. So A is still an m by n matrix, and the following are equivalent. So I should say this was max rank in the sense of, we have m columns in rows. Now we want this to be max in the sense of m, right? So max in sense of the codomain, not the domain here. So 1, now we're going to look at when the rank of A is maximum in the codomain, right? So meaning we have rank m here. Well, then the column space is just Rm, right? And it's really, we're just going through an analogous theorem, but now for the codomain instead of the domain, right? So 3, we have that the rows of A are linearly independent in Rn. We have that A transpose is an m by m invertible matrix. We have that there exists an n by m matrix C such that now it's when you flip the order, right? So if you multiply by C on the right, you get the identity matrix in the codomain in Rm. And lastly, we have that AX equals B is consistent, meaning there's always a solution for every vector B in Rm. And what does this mean? This last statement here means, so if you have a max rank, right? If you have rank m here, then this means that the codomain equals the image of A. That's what this last statement is saying here, right? It means that for every, it means, well, we'll learn what it means. It means it's surjective. For a map to be surjective, it means the codomain or the image is the entire codomain, right? And so basically what it's saying is like every vector B in Rm, like every point in Rm is being hit under this map by some other vector X. Okay, and that's what we're saying here. Again, if like the surjectivity thing here sounded a little confusing, that's fine because we'll define that and discuss it more rigorously later. Okay, I think this is all I wanted to discuss about the rank, null space, and image for now. Where we're going to go from here is we're going to start to take a look at orthogonal matrices. We'll have this notion of orthogonality that's in line with our understanding of what it means to be orthogonal, right? Or normal or perpendicular. So From here, we're going to start to take a look at orthogonal matrices.